left the notes that we were using, obviously, the notes we were following last time are in my office. So instead of picking up where we left off directly, today I am going to go through essentially derivation of the Reynolds average Navier-Stokes equations, and then maybe also talk about large eddy simulations a little bit. So we'll do that today, which was my plan anyways, but it's just a little bit discontinuous here. So we're going to do Reynolds averaged Navier-Stokes.
As long as it's discontinuous and doesn't diverge. Sorry, I couldn't resist.
You never know. Well, look, now it has diverged.
You're welcome. Just got to decrease the time step a little bit.
So this is RANS. If anybody has ever heard of RANS, we're going to be talking about RANS. So what we are going to do essentially is we are going to follow this approach. So we are going to replace full field variables in the conservation equations with their Reynolds decomposition representation. All right, so all I mean is that everywhere U appears in the equations, we have the average U plus a fluctuation in U. So this is step one, and then we'll also have pressure is equal to the average pressure plus a pressure fluctuation. And then we're gonna, okay, so I guess I should say this is for incompressible flows. So if you had a compressible flow, you'd also have a Reynolds decomposition for density as well. Okay. And then the second, so once we've done that, the second thing we're going to do is we're going to average the entire expression. Okay. Just to remind you, we are going to, so some reminders. So we are going to just use a time average. So everything will be spatially variable in this derivation, and the angled brackets are only going to mean the time average. So we'll let the angled bracket be a time average. So essentially, angle bracket U is by definition going to be 1 over delta t, integral from t naught to t naught plus delta t u dt. Okay, so just a time average. I'm also going to remind you of some rules that will be handy. So if we have some fluctuating quantity f prime, the time average of that thing is by definition 0. If we have an average quantity times a full field quantity, and we average that whole thing, that is equal to the multiplication of the average of both things. You can think of this rule as mean F is just a constant, so it can come out of the average, is what's happened there. We'll also make use of this rule. So the mean of the average of two summed quantities is the sum of the averages. And we'll also use the rule that if we have the average of a derivative, it's the same as the derivative of the averaged quantity. And then last but not least, if we have two fluctuating quantities multiplied with each other, this is not equal to 0. Okay? Okay, great. Okay, so let's start with the continuity equation. So conservation of mass. Which we know and love. So we have and this is for an incompressible flow. All right, so we just have that the divergence of the velocity field is 0. So I'm going to substitute in the Reynolds decomposition for UI. So UI is going to be equal to the average of UI plus a fluctuation component. And I'm going to substitute that in here. And that's also equal to 0. And then I can distribute this derivative. Right? And so this was step 1. And step 2 is I'm going to take the average of equation 1. So this is equation 1. So I have the following. Oop. All right, so I'm just going to distribute that averaging operation. So I have this plus this. And then, of course, I can bring that average inside of the derivative, which was one of the rules I just wrote. So this is partial xi of the average of ui plus partial xi average of ui prime is equal to 0. Average of an average is the same, so unchanging. And mean of a fluctuating quantity is always 0, which means we have this final version of the equation. Okay, so this is our final version of conservation of mass. So it turns out that for conservation of mass, it's not very exciting. We just have that the divergence of the mean velocity also has to be equal to 0. Okay, by extension, so since we have that partial ui, partial xi is equal to 0, partial average ui partial xi equals 0. And I need more space. Hang on. Please hold. Hang on. Okay, let me move that. And then we also have the definition that ui is equal to mean ui plus ui fluctuation. So all those things together imply that the divergence of the fluctuating velocity is also 0. Okay, so all components of this Reynolds decomposition satisfy continuity. So we have that the full field velocity has to be divergence free, the mean velocity has to be divergence free, and the fluctuating parts of the velocity have to be divergence free. So,
Sorry, one quick
yeah.
question. So we get rid of we can just assume it's statistically steady because we've done a temporal average and we just assume that that's the case. So that's why the time derivative component
Oh, it's
of
incompressible.
density. Oh,
It's
okay,
a,
okay.
yeah. Yep. So, this doesn't necessarily need to be steady, if that makes sense.
Yeah, it makes
So
sense.
we,
I went on a little mental journey and realized that it was density, that it was the time derivative of, which, like you said, incompressibility. That was my bad.
no, it's okay. I mean, it can be ambiguous. Okay, so this means that UI average, and UI prime all satisfy continuity, which is kind of a cool result. I don't know about you guys, but it would not have been immediately obvious to me that the velocity fluctuations would satisfy continuity. Obviously, it didn't take a long time to prove that, but there we go. Fun result. Okay, we're going to do the exact same process with the momentum equation. Which is Navier-Stokes. Okay, so our equation is that dt of ui plus uj partial ui partial xj is equal to 1 over rho partial p partial xi plus nu Laplacian of ui partial xj squared. Okay, so this is just Navier-Stokes equations. I have not included any sort of external forcing in this one. Which, yeah, so we're doing the kind of the simplest flavor of incompressible Navier-Stokes here. So I am going to let ui equal average of ui plus its fluctuating component. And I'm also going to let pressure equal the mean pressure plus a fluctuating component. Okay, and we're going to substitute. Is that right? It looks like too many T's. I think that's right. Substitute
That's right.
these expansions into Navier-Stokes. All right, so I have partial T of ui plus average plus the fluctuating part plus mean of uj plus uj fluctuation partial xj of mean ui plus the fluctuating part of ui is equal to 1 over rho, which we're assuming to be a constant, partial xi of mean pressure plus the fluctuating pressure plus nu times the second derivative with respect to xj of mean ui plus ui prime. Are you feeling re-traumatized yet, Lee?
Very. I'm just waiting for
Okay.
there to be three components in there.
What's that?
I'm just waiting for there to be a trinomial somewhere.
Ah, yes. Just wait.
But wait,
Okay.
there's more.
But wait, there's more. Okay, so I'm going to expand out these terms. Um, I think I'm going to do it term by term. Let me see the best way to organize this. Okay, so we're going to go term by term and expand out, then take the average of it. Okay, so I'm going to do the unstudied term, we're going to do in pink. So we'll do this guy first. Ow. Oh my gosh. There, okay, that took forever. All right, so I have partial t of ui plus partial t of ui prime. And then I'm going to average this whole thing, which means I have average of partial t average ui plus average of partial t ui prime. And then I'm going to bring that average operation inside of the derivative. So I have partial t average of the average of ui plus partial t average of ui prime, which of course is 0. So this guy is by definition 0. And then this guy is just the same as the average of ui. So we have partial ui, average ui, partial t, and that is the final result for that term. I'm going to strategically avoid the next term and I'm going to do it last.
Why?
It's more involved. I just want to do it last. Just let me
I
have
was
this, Lee, okay?
I was just being sarcastic, yeah, because you
Don't
asked me.
spoil it. Don't
I'm
spoil it.
sorry.
Okay. The green one, I am going to have minus 1 over rho times the quantity of partial mean p partial xi. Oops, not yet. Plus partial p prime partial xi. Same sort of deal here. So I'm going to distribute this average. And actually, I'm going to bring the 1 over rho outside because that's a constant. So I can take a constant out of the averaging operation, just like I can take it out of an integral or a derivative. And so I have the average of partial average p partial xi plus the average of partial p prime partial xi. And this is equal to 1 over rho quantity partial xi of the average of p, which is just average of p, and then partial xi of the average of p prime, which by definition is 0. And then this guy is just the average of p. So we have here minus 1 over rho partial xi of the mean pressure field. Okay. I also have this diffusion term, viscous diffusion term. And we will take the Reynolds average of that term, nu times the Laplacian of the mean velocity plus the Laplacian of the velocity fluctuations. And we end up with the viscosity. I'm going to pull out of the average because it's a constant. We have the average of the Laplacian of mean velocity plus the average of the Laplacian of the velocity fluctuations, which is, I can bring in the averages into those derivatives. So I have the Laplacian of the average of u plus the Laplacian of the average of the velocity fluctuations. Hopefully you are seeing a pattern at this point. So this is by definition 0 again. And then this guy is just the same as the average of the velocity field. So this one, we just end up with nu times the Laplacian of the mean velocity. And then last but certainly not least, have to give it a good color. Hang on. Let's pick a good color for that one.
Red because of rage.
Red? No, we love this term. Let's color it orange. That's a good color.
Yeah, serve as a warning.
Fun times ahead. Warning, fun times ahead.
Yep, let's go with that.
Okay, so we have our convective term now. So we are going to do the average of average u plus fluctuations in u, that quantity times the divergence of average u plus the fluctuations in u. All right, so first things first is I'm going to expand out this whole thing. So I have average uj times partial average u partial j plus average u times partial xj of ui prime plus uj prime partial xj ui prime. Nope, that wasn't the order I wanted. Mean ui plus uj prime partial xj of ui. Oh, goodness. Ui prime. Okay, great. And then I'm going to distribute that averaging operation out. All right, so we have that this is equal to the average of this first term plus the average of the second term plus the average of the third term plus the average of the fourth term. Okay. Anywhere I have an average inside of an average, I can consider that to be a constant and I can pull it out front. So what I mean by that is This term can get pulled out of the average. This term can be pulled out of the average. And then this term can be pulled out of the average. So I'm going to do that now. So I have average uj times partial xj of the average of ui. I'm going to skip that step where I say average of uj is uj. Average. Then I have uj partial ui prime partial xj. Actually, hang on. I'm going to pull that into the differential again. Plus partial ui partial xj average uj prime plus this thing. Okay, so couple convenient things. This is by definition 0, and this is by definition 0. So those two terms go away. Hang on. One moment. Okay, this is fine. And then, so I have remaining this term, and then I have this term. Okay, where the second one is something famous that we'll talk about in just a second. So I am going to manipulate this just a little bit. So I would like this to be in the form that looks like this. Because then I can put the average inside of that derivative. Oops. I wanted this to be an angled bracket, not a parentheses. Okay, I would like it to be like this. And so I'm going to just do the product rule to kind of get us to that spot. So I'm just going to do the product rule here. So I have ui prime partial uj prime partial xj plus uj prime partial ui prime partial xj. Where this second one is what we have. Mhm. Let me make sure I didn't skip a step here that turned me around. Mhm. One moment. Mhm. Ugh. Does anybody see what I'm missing? Did I skip a step?
No, because I think it when you put everything back together, you would be able to undo the product rule and you would get the partial x j of ui uj or average ui uj, and then but there's a negative sign that appeared somewhere.
Well, I so like this should work out to be so this should be it should be this in the end, but I'm trying to figure out and I know I don't this is not incorrect. So like this is not incorrect. I'm just trying to figure out what I'm missing to get from this to this. Because let's see, let's keep going. Hang on. Maybe so our UJ, oops, not different color. So UJ prime partial UI prime partial XJ is equal to partial XJ UI prime UJ prime minus I prime partial UJ prime partial XJ. And then if I average both sides, oh, that's what it is. This is equal to 0 due to continuity, right? So if you remember before, we said that this was true. What will be a not horrible color? Uh, purple? That's not bad. Okay, so we said this was true, right? So that means that this is equal to 0. And so we can rewrite, thought I was losing it, guys. Okay, so we can rewrite that term that we already came up with as this. All right, so that's how we go from here to here. Hopefully that makes sense. Does that make sense to everybody?
kind of. Since you're multiplying by UI, though, does that still hold?
Say again?
Does that still hold? Because since you're like you're taking the average of UI prime times that, like
Oh, but
the
so this equals zero from continuity has nothing to do with the average though. Like we already know that the divergence of the fluctuating velocity always has to be zero, right?
but
Like
yeah,
this,
I guess
sorry, go ahead.
no, I guess it makes sense now that like you're multiplying something that's not necessarily directly related to it by like you're multiplying the divergence by something outside that term.
Yeah, so like if we had like the average of 3 times 0, that average is always zero, right?
I think my big thing is that like since the divergence is basically a sum, you're multiplying uh, non-constant quantity times a sum.
Um, but the sum always sums to zero, right?
Yeah, that makes sense. I guess each component of UI prime has to get multiplied by the entirety of the sum. Okay, yeah, that makes sense.
Yep. Yeah, so you can think of divergence as just like a constant. Because full circle, repeated index means that it's a scalar, right?
Yeah, that makes sense.
Yay. Okay, great. Okay. All right. So that was a journey, but this term is then uj partial average ui partial xj plus partial j of ui prime uj prime, where this term, the second term, is a special quantity called the Reynolds stress. Okay. Um, the Reynolds stress. Hang on. Let me just I'm gonna. Okay. Hang on. Let me rewrite the resulting equation now. That first one was pink, right? So we have partial average u partial t plus average uj partial average ui partial xj plus partial xj of the Reynolds stress. And that is equal to minus 1 over rho partial xi of the average pressure plus, oh, I didn't do the colors. Hang on. Green. Minus 1 over rho gradient of the mean pressure plus nu times the Laplacian of the mean velocity. Yes. Okay, so this is our resulting expression, which you'll notice is the same as regular Navier-Stokes, but with the mean quantities as argument, except for this term in orange that we got, or part of this term in orange that we got here. So let me just write that down. So these terms all together, this is Navier-Stokes with mean quantities as argument. But we've ended up with something extra. All right, and that extra term is going to cause some challenges for us. And the reason for that is because the whole point of doing this was we wanted to get a set of equations that are going to govern the physics of our system, but in an average sense. So the idea is that we would like to solve these equations potentially instead of like the full field system of equations, which would require a really tiny mesh and really small time steps. It is often beneficial to us to speak in terms of mean quantities instead. So that means that when we're solving these equations, the variables that we are solving for are average velocity and average pressure. Okay. So when those terms appear in our equations, that's just fine and dandy because we're planning to solve these equations. But we ended up with this Reynolds stress term, which is a quantity that's not one of our variables that we plan to solve for, which means we need a model for it. Okay. Um, and then, oh, you know what? Why don't I'm going to rearrange this equation a little bit so you can see how it's traditionally presented. So this equation is usually algebraically manipulated into the following form. All right, so I'm going to keep most of these terms untouched, but I'm going to take my Reynolds stress term and I'm going to put it into the viscous term, essentially. All right, so I keep this term the same. And then I have my minus 1 over rho, partial xi, mean p, plus I'm going to separate my Laplacian into like a two-step derivative situation. So I have nu partial average velocity partial xj minus my Reynolds stress. Okay, so that is generally how.
Don't we need to have a one over the uh, one over new in front of the Reynolds stress term?
No.
Oh, never mind. Sorry. I saw you didn't bring up front. My bad.
It's okay. I didn't make a mistake this time.
Oh, that was my will.
Um,
Sorry.
yeah. The key thing is that this term needs a model. All right. And it is a second order tensor. So essentially, we have introduced 6 new unknowns into this. And this is often called the closure problem. I don't actually know the origins of this, but in the turbulence community, closures are like saying something is a closure is another way of saying it's a model. Um, so if a set of equations is closed, that means that we have the same number of variables as or same number of equations as unknowns. If we have more unknowns than we have equations, then it is unclosed. Um, and actually, oh, I wonder if I can find it. My PhD advisor had a cartoon in his office, and it was something like let me see if I can sketch it. It was cute though. It was like I don't know if I'm gonna be able to do this justice. Okay, so it was like a door, and the door was open. And then on the door it had, and then it said, please close before leaving, which I thought was hilarious because this is very hard to do. So, uh,
don't know if you mentioned it yet or if you haven't gotten there yet, but like the reason why there's six terms instead of nine is the because of the symmetry.
yes. Okay, yes. Yes. Okay, so let's talk about that. Um, so we now have six unknowns without a corresponding equation. Okay, the reason that there are six instead of nine is the following. So if I write out this tensor, I have the following. So I have uh, UU, UV, UW, VU, VV, VW, WU, WV, and WW. All right, and so it turns out that it doesn't matter the order in which you multiply these things. So UV and VU are the same, and UW and WU are the same, and VW, WV, these are all the same. Okay, so that is three unknowns. So we have one, two, three, and then our diagonal terms are all unique. 4, 5, and 6. All right, so it's 6 because this is a symmetric tensor.
Sorry, I hope I didn't get ahead of you. I just like having
No,
flashbacks
I
to all the
forgot
things
that I
I
was going to say it. It's okay.
awesome.
Um, okay. Uh, Another way of writing that is you can say that ui prime uj prime is the exact same thing as uj prime ui prime, right? Okay, so because of this, we have, this means we now have four equations. So conservation of mass, and then 2 through 4 is conservation of momentum, right? Because that's a vector valued equation. But we have 10 unknowns, which is generally not a good place to be. So our 10 unknowns are U, V, W, P, and UU, UV, UW, PW, PV, and WW. Okay. Okay, so based on this, turbulence modeling, or the goal of turbulence modeling, is to define, aka model, or close the Reynolds stress term in terms of known flow variables. All right, so the name of the game is essentially to find an expression for this as a function of our known flow variables, which is the average velocity and the pressure. Okay, any questions so far? No? Okay, let's talk about some common closures. These are historical closures. Okay, the first one that I'm going to talk about is the Boussinesq eddy viscosity hypothesis. So this is most common. This was developed in 1877. Sometimes the Boussinesq out front is dropped and it's just called an eddy viscosity model. All right, and so this model looks like the following. So it says that the negative of rho ui prime uj prime is equal to 2 mu t sij minus 2/3 rho delta ij k. And I want to check on something really quick. Oh, okay, actually, I have a question. Julien, this is a French name. I'm sure I'm butchering it. How do you say this last name?
I would say, uh, yeah, actually, I don't know.
Oh, no?
Bussinesque?
Oh, okay,
Bussinesque?
so I wasn't
Yeah,
so far off.
Bussinesque, I would say, yeah.
Okay, great. All right, I haven't been butchering it as badly as I assumed.
Yeah,
That's good.
that's so good.
Okay, so let's talk about a couple of the things in this closure. So the first one is this is our turbulent viscosity. That's why we're calling it mu sub t. We also have this term S, which is a tensor. Um, and this is the mean strain tensor. And it is just defined as the following. So it is 1/2 the gradient of the mean velocity plus its transpose. All right, so that exists all in terms of our mean flow quantities because it's all in terms of um, average velocity. And rho is just density. Chronic or delta is just the identity matrix, like we've seen before. And then K is the turbulent kinetic energy. And it is just 1/2 the trace of the Reynolds stress tensor, which you can also just write as 1/2 UK, UK. Okay? Okay, so let's talk about the physical justification for this model. Okay, so when we have laminar flows, energy dissipation and momentum transport normal to the streamlines are governed by viscosity. So the idea was that we could represent turbulent effects on the mean flow as basically just an increased viscosity. So kind of a like an extra contribution to what we would see in a laminar flow. It is worsened in a turbulent flow, so we can kind of lump it together um, and explain it in that way. So let me just write that down. So in laminar flows, energy dissipation and momentum transport normal to the streamlines are governed by viscosity. So by extension to that, we are going to represent turbulent effects on the mean flow as an increased viscosity.
I don't know if this is necessarily within the scope of this discussion, but like, is it basically just because it affects the energy cascade, or is it actually acting like it's either enhancing or inhibiting the shear just because of all like the localized turbulence?
So I'm trying to remember. I feel like to adequately answer this question, I should know kind of how Buzinesk came up with this form of the model. Uh, I assume in 1877 it was experimentally related. So I don't know that I have a good answer for that question at the moment, actually.
No
I
worries.
think it
I
was,
was just kind of curious.
yeah, no, 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 it's okay. I mean, I think probably I'll look into this and correct it if I'm wrong, but I think likely the case is that, scientists at that period of time were comparing, uh, laminar flows to turbulent flows and then noticing kind of what happens is similar to what would happen if it was still laminar but had a higher viscosity, if that makes sense.
Yeah, it makes sense. So it's basically just like inhibiting or it's creating more resistance to shear, just because of the localized turbulent movements.
Mm-hmm. So, so if we use this model, uh, if we put this into our Rand's equation, it looks like the following. So we have rho times our material derivative of the mean velocity is equal to minus the gradient of the mean pressure plus the divergence of two times the, oops, sorry, two times the actual fluid viscosity of that mean rate of shear tensor minus, I'm going to keep this as, so here's our term that we want to put in our model for. So we want to put in our closure for this guy. All right, so I've just reformulated our viscous term in terms of the mean rate of shear tensor. All right, so that means that I can rewrite this as minus the gradient of our mean pressure plus the divergence of the quantity 2 plus our viscosity plus a turbulent viscosity times Sij. And then minus, we have that 2/3, the trace part that comes off. Okay. Okay, so now that we have the form of this model, the issue is the following. So now our closure problem boils down to specifying what that turbulent viscosity is and the turbulent kinetic energy. So we've gone from 4 equations and 10 unknowns to 4 equations and 6 unknowns, right? Okay, so there are essentially 3 different approaches to sorting this out. And they are the following. So the first one is called the zero equation approach. You can also think of this as an algebraic closure. All right, so there's a few flavors of this. So one is the use of a expression for turbulent viscosity that looks like this. So you have some constant coefficient C mu rho ut times L. And here the Cu is a problem dependent constant. L is a prescribed length based on grid location. Usually the distance from a wall. And the characteristic velocity can be found in the following way. So for 2D, as the following. So we have ut is equal to L times partial u partial y, for example. and then of course rho is density. So the Baldwin-Lomax model, which was developed in 78, is a standard algebraic model. And it works well for thin attached boundary layers. I should also mention that this form that I put here, this form is based off of dimensional analysis. Which was done using a Prandtl mixing length. And that work was done in 1925. I'll also, we're pretty much done with class now because we're at time, but I will make the note that Prandtl did really good science and helped the fluids community tremendously with his contributions, but he was a terrible dude.
Absolutely
And
an awful person. 0 out of 10.
yeah, 0 out of 10. He was a Nazi sympathizer. uh, so yeah, you can do really great science, but also be a horrible human being, and he is one of them. So, are there any questions on this though? If not, I will let you go, and then we will pick this up again next time.